Hello and welcome. In this lecture, let us see how to obtain Schrodinger wave equation. So, when de Broglie gave his hypothesis of wave-particle duality, then there is a necessity to develop mathematics to understand that. And so, in that regard, Schrodinger came up with his wave equation. So, it all started by considering a simplest type of wave, that is a plain monochromatic wave, which is going in three dimensions, which exists in three dimensions. So, so the equation of that plain monochromatic wave is psi of r comma t, where r is the position given as a kr minus omega t. So here, this is a complex quantity. As you can see here, it is has real and imaginary components. So, and the coordinates are space coordinates as well as time coordinate t. So here r is a position in three dimensions which have x, y, z components. Now, for simplicity, just for obtaining the Schrodinger equation, let's consider one dimension, that is propagating in the x-axis. Then we may extrapolate that to three dimension. It's just minimizing the amount of writing. Other than that, we can easily extrapolate uh, this to three dimensions. So this is a plain monochromatic wave moving in x-axis along the x direction. Now here we have k and omega. K, k is the wave vector. So as it is a vector uh, moving along x direction, so I am taking x cap, denoting the same direction along the x axis. And we know that momentum p is equal to h cross k, basically h by 2 pi. Here k is 2 wave vector, which is 2 pi by lambda. So this corresponds to h by lambda. And we know that energy is equal to h nu. Now if we divide um, h by 2 pi and multiply frequency with 2 pi p, then we get h cross omega. So this will yield us k is equal to p by h cross, whereas this will yield omega is equal to e by h cross. Now let's substitute wave vector k and angular frequency omega in the equation 1 here. So let's consider this as equation 1, and substituting k and omega in the equation 1. So what would we get? Psi of x comma t equal to, so we got p is equal to um, So K is equal to P by H cross X minus omega is E by H cross T. So we end up getting A I by H cross. I'm taking H bar common. So we get Px minus Et. So this is a wave function. Now, when we do partial differentiation of this wave function with respect to time, that is dou psi of x comma t by dou t, we get a so we are partial differentiating with respect to t, so we get minus e here minus e along with it is multiplied with the I by h cross. So take care of that. That also will come in this. So now from above we know that a e power I by h cross px minus et. So this is nothing but the wave function psi itself. So this is all psi of x comma t from the above and multiplied with this one. So we get minus um, I by h cross e into psi. Now when we take this to other side, we get h cross by minus I. H cross by minus I is nothing but I. So basically, when we do this minus I dou psi of dou t, this will give us which is which gives us I h cross dou psi by dou t is equal to E psi. So we end up with the relation between partial derivative of partial time derivative of wave function and energy. So we obtained a relation for energy. So this is a mathematical correlation for energy that we obtained from the wave function. We can also partially differentiate the wave function with respect to x. So I'm not writing that. So we have a here I by h bar px minus um, et. Basically p by h bar is k and e by h bar is omega multiplied with I p by h bar. So this will yield us. So this is again equal to psi. So by rearranging the terms, we get h bar by I dou psi by dou x equal to p psi. But h bar by I is nothing but minus I h cross. So with this we got the relation for momentum. So we got both energy and momentum when we partially differentiate with time and position respectively. Now let's double derivative the wave function. So when we do that, that is dou by dou x of dou psi by dou x. Then this will give us um, so basically we are differentiating this one. When we do that, already we have I p by h cross, and when we derive that, we will get a again I by h cross into p e power I by h cross px minus et. So but we know that a times e power I by h cross px minus et is psi. So from this we get dou square psi by dou x square equal to I into I is I square, which is minus 1. So we get p by minus p by h cut square. And as we know, a times that will that exponential will give psi. So sorry, here p times p we have, that is p square. Now we may rearrange like minus minus h cut square dou square by dou x square is equal to p square psi. Now let's divide the above equation with 2m. So by doing that, we get minus h square by 2m dou square psi by dou x square is equal to p square by 2m psi. So here we can see that p square by 2m is nothing but kinetic energy, and this kinetic energy and momentum relation. So basically, this is of the non-relativistic free particle. So non-relativistic free particle. When a particle is non-relativistic and its free particle, then kinetic energy would be p square by 2m, where p is the momentum and m is the mass of that particle. So basically, this Schrodinger wave equation which is developed, it is applicable for non-relativistic mechanics, non-relativistic phenomena. So, what is a free particle? A free particle which is not subjected to external force or external momentum. So, basically, the potential. So, if it is a free particle, when a particle is said as free particle, then its potential would be zero. Basically, potential is zero. That implies no external force. No, for example, gravitational force or electromagnetic force, force due to electric field or magnetic field, and so forth. So, when a particle is not subjected to any of those forces, then it is a free particle. And just a definition of what free particle is, which is very important to distinguish it from the potentials and so forth. So, so for a free particle and non-relativistic, we have seen that kinetic energy is equal to p square by 2m. See, total energy is sum of kinetic energy and potential energy, but for a free particle, the potential energy is zero. So this will end up p square by 2m. Now, when we substitute in the above equation 2, now by substituting the e into, we get minus by 2m dou square psi by dou x square, which is equal to e psi. So this is third equation. So initially we have derived partially with respect to time, and we got this equation. So for energy, we got IH cut dou psi by dou t, and here in this case we got this equation. So now for a free particle, we can equate these two equations. So the equation I haven't numbered there, but we remember that. So I sorry IH cross dou psi by dou t is equal to E psi, which is equal to minus h cut square by 2m dou square psi by dou x square. So now this is a Schrodinger equation, and this is a Schrodinger equation for one dimension, because we it is the wave function is only propagating along x-axis. One dimension time dependent Schrodinger equation for free particle. So in the exam, if suppose this equation is given and it is in the options, they are asked which equation is that, it is easy to identify the um, that the equation of what, it is easy to identify that it is the equation of free particle, because there is no potential energy component in this. So as the from the equation itself we can apparently see that there is total energy on this side, and there is kinetic energy on this side, and there is no potential energy. So that implies this is a free particle. Secondly, whether it is relativistic or non-relativistic, that can also be seen from here, because uh, the kinetic energy which is represented is related with momentum, that is p square by 2m. So hence uh, this is of non-relativistic. So now, at this stage, we are good to learn two operators, to identify two operators. So, firstly, let us know what is an operator. So, in quantum mechanics, operator means something that operates on wave function and gives us result. Uh, Something that operates on wave function and it gives us result. Suppose if that operator gives us energy, then it is energy operator. If it gives momentum, then it is a momentum operator. So we have identified that I h cross dou psi by dou t is equal to e psi. So now here we are getting energy times the wave function, and on the left hand side we have I h cross dou by dou t of psi. So this psi and this psi are equivalent. Hence, when we operate on that operator, we get energy and the wave function. So here energy operator is I h cross dou by dou t. So it's very easy to remember these operators when we I understand the concept of obtaining the Schrodinger equation and getting the relations for energy, momentum, etc. So now it's very obvious regarding the momentum operator. So we have seen by derivating the wave function, partial derivating. If you remember the monochromatic plane wave along the x-axis. So for one dimension case, we can easily recollect that when we do this partial derivative, we will get I by h cross um, p times psi. So when we take h cross that side and divide by I, so basically multiply I and I in the denominator, getting minus h cross. Um, Sorry, we are, yeah, minus h cross. We are taking that, and this is minus I. and dou by dou x times psi will give us momentum times wave function. So here momentum operator is minus I h cross dou by dou x. So it is also easy to find the kinetic energy operator and so forth. Now we have seen that only for one dimensional case, but we can extrapolate the same to three dimensions. So in case of three dimensions, what will be the momentum operator? That will be minus I h cross del. So here del is nothing but del is equal to dou by dou x plus dou by dou y plus dou by dou z. So three dimensions case. And we can also find momentum along each axis, momentum operator along each axis. So px minus ih cross dou by and along y. So the total momentum p is nothing but under root px square. When we calculate the 3, we can do this to get the momentum of the system. Okay, let's continue our discussion. So we have seen free particle case. Now let us consider the particle is present in a field characterized by a potential energy function uh, V of r comma t. So basically, the potential is dependent on both the space coordinates and time. And we know that for non-relativistic case, E is equal to p square by 2m plus v of r comma t. Um, so and E is I h cross dou psi by dou t and p square by 2m. We have seen that p square by 2m. So we have seen the p square by 2m. Let me get back to that. Mm, yeah, here. So when we okay, from here you can see minus dou square by dou x square is equal to p square by 2m psi. And this is equal to, yeah, right. So here we got p square psi and minus h cut squared, and when we divide with 2m on this right hand side we get kinetic energy p square by 2m times psi. Also we have the um, equation here, IH cross dou psi by dou t is equal to E psi. So basically it is E times psi. So IH cross does nothing but E psi. Uh, and we know that E is nothing but P square by 2m plus V of R comma T, because there is potential energy also, times psi. So here we got this from the very first equation which we derived. So we are just substituting the non-relativistic case energy here. Now we have to see p square by 2m times the psi. So that will be yeah, p square by 2m times psi is nothing but minus h cross square by 2m dou square psi by dou x square in the second equation. So this equals to minus h square 2m by dou square psi by dou x square, p square by 2m into psi. And then this one is v times psi. Remember that v and psi both are functions of space and time coordinates, but for simplicity I'm just writing it as v psi. And here we have I h cross dou psi by dou t. So this is it. So now we have obtained the Schrodinger equation for a particle in a field. So, so how we obtain the Schrodinger wave equation? We obtained by putting corpuscular and wave characteristics together and assumed that wave function uh, and assumed that the particle can be described by a wave function psi, and which is generally complex. So by putting appropriate boundary conditions as well as initial conditions, so where from where the system started and so forth, reflecting the initial conditions and also the boundary conditions, the existence of potential along the space coordinates, like the boundary of potential within the space coordinates, etc., and that will help us to predict the results of different measurements. And we you might have known that the Hamiltonian is nothing but the sum of kinetic energy and potential energy. So H equal to P square by 2m plus V. So we have V psi and P square by 2m psi. So um, we can represent I H cross dou psi by dou t equals to uh, minus h cut square by 2m. So this will be Hamiltonian times psi. I'm taking psi as common. Then this that will be equal to Hamiltonian. So here h is also an operator called Hamiltonian operator. So till now we have learned three operators: energy operator, momentum operator, and Hamiltonian operator. So Hamiltonian operator is minus h cut square by 2m dou square by dou x square plus v. This is the Hamiltonian operator, and this is acting on the wave function just like energy and momentum. However, so theoretically, the Schrodinger wave equation is obtained, but it is consistent with the experimental results. So the experimental data is consistent with the theoretical results that are calculated using the Schrodinger wave equation that we obtained. So yeah, this is how we obtain Schrodinger wave equation, and we have seen the operators and time dependent Schrodinger equation. We have seen for free particle and also for a particle in potential in some field. Um, in the next lecture, we will continue the discussion on Schrodinger wave equation, and we will see more interesting concepts. Thank you so much for watching.